Hey guys, Mrs. Bodechon here. So we're going to look at our AKS portfolio for radioactivity, and we're going to go ahead and start with 4A. It says, I can develop a model that illustrates how the nucleus changes as a result of fusion and fission. So if we look at your sheet, you have fusion and fission, and then you are needed to give the definition, an example, and complete this model. So the model's been started for you, and it's saying, hey, what else is it going to look like as a result of fusion and fission? So let's first talk about what they each are. We're going to start with fission, okay? So fission is where we take and we split a larger atom into two or more smaller atoms. So you can see this is our large atom right here. And what we do is we hit it with a neutron. A neutron comes and it smacks it, okay? And it ends up breaking it into two smaller pieces. And that's where you can see these here. All right, so if I were to add up the mass of this piece and the mass of this piece, it would equal my starting piece, all right? Now to go over to what fusion is going to be the opposite. So in fusion, we are joining two or more lighter atoms into a larger one. So you can see our two light atoms, and they're coming together and they're fusing into one big chunk, okay? So let's look at some more specifics on this. So fission, we do use in nuclear power plants to produce electricity. All right, it does occur in the sun as well, or other stars for that matter. And we do use it to make nuclear weapons, right, like bombs and things like that. Not all bombs are nuclear bombs, okay? I'm talking about just like atomic bombs. Fusion, on the other hand, is completely different. Okay, fusion is a lot more powerful. It does also occur in the sun and a lot more than fission does, or other stars for that matter. It requires a very high temperature with a lot of pressure, too much. So we don't actually use this in our power plants at all. We just can't reach that high of enough temperature with the pressure in order to use it, even though it does release tons more energy than fission. So if someday we can harness fusion to make electricity, we're really doing ourselves a favor, okay? So here is the completed models that you were supposed to go ahead and draw. And you can see this is pretty much exactly what we looked at already. So here we have fusion, two smaller ones, giving you the bigger one right here. And you can see that this is a neutron, here's helium, and here's energy. It's just in this particular case, you guys, okay? Now this one over here is going to be fission. So you can see that we're having a neutron come and hit uranium. Okay, uranium because it's U. And then you can see what's happening here, and it's kind of creating like a chain reaction. Okay, so we're going to kind of switch gears, and we're going to talk about nuclear decay now, all right? So on your sheet, you can see you have a table with alpha, beta, and gamma rays, but these are particles. Alpha and beta are particles, gamma is a ray. And you need to give a description, the change in mass, change in atomic number, and what it can be stopped by, okay? These are all forms of nuclear radiation, nuclear decay that occur. So before we even get into this, let's talk about what it is and what it can be stopped by, okay? So here is a little diagram for you of each one. You can see we have paper, aluminum, and lead, right? Our alpha particle is kind of like the nucleus of a helium atom. Okay, it's two protons, two neutrons, as you can see demonstrated right here. So it's pretty big in terms of these three, and it can only actually penetrate, I mean, it can go through your skin. If it gets on your skin, it can go through it and be absorbed and things like that. But you can block it so easily. In fact, you can block it with just a sheet of paper. And so here's a piece of paper, and you can see that it's not going through it. All right. A beta particle is actually just one electron. And that's the electron it's showing you right there. It's just one teeny tiny little electron, much smaller than an alpha particle. And its penetrating power is, it's a little bit more than an alpha particle. It can go through a sheet of paper, but it can be stopped by a thin sheet of aluminum foil. Okay, so here's our sheet of aluminum foil, and you can see that it cannot go through that. Now we have gamma rays. Gamma rays are not a particle, they are a wave. So you can see this is a wave, right? And because it's a wave, it can pretty much go through anything, all right? Can't be stopped, and they're incredibly dangerous for that matter. So we can see it goes all the way through paper, all the way through aluminum foil, no problem. In fact, it goes the majority way through lead. And look how thick this lead is, you guys. This lead is really thick. It can go all the way through lead. It does stop a little bit. Notice it does stop a little bit, but some of it still gets through, okay? So if we go back over to our chart, let's go through each one individually. So we're going to look at alpha first, okay? So yes, it is a helium nuclei. The symbol is He for helium, and then you're going to write a 4 superscript and a 2 subscripts, all right? And let's talk about what these mean, these 4 and the 2. So the mass is the 4, because a helium is 2 protons, 2 neutrons, so it's 4 AMU, okay? So that's going to be our mass number. And then the 2 is going to be how many protons it has, okay? So the atomic number is 2. So that's going to be what the 2 represents there. And what can it be stopped by? By a sheet of paper, absolutely. So let's go ahead and move on to beta. Beta, as I said, is an electron. We do have the symbol B for beta, and the numbering, the superscript, is going to be 0 because there's no mass to an electron. That's worth noting, right? So we're just going to call it 0. And then the bottom number, instead of the number of protons, this is going to be based on the change in atomic number. So it's going to be increased by 1. What we're going to end up writing is a -1 because it's an electron, right? It has a charge of -1. So when we end up doing this math of nuclear decay, we need it to say -1 because it's going to impact that, all right? And I'm going to show you in a second. And what can it be stopped by? It can be stopped by a sheet of aluminum foil. And then gamma ray is our last one. And gamma ray has this funky Y, right? It is photons, or you can say waves, because it is just a wave. And this is the easiest one to remember, 0, 0. Superscript and subscript 0, 0, all right? There is no change in mass. It's a wave. It doesn't have mass, so 0, right? And it doesn't have any effect on the atomic number, charge, nothing, because it's a wave. So everything is a 0. It's not a particle at all. And what can it be stopped by? Thick lead or concrete, mostly. And remember, not all of it can be stopped by that, just most of it, okay? So let's continue on. So now it's asking you to actually decay some things. So it says alpha, beta, and gamma decay uranium. So we're going to go ahead and decay these, okay? So if you're looking at alpha decay, what we're doing is we're writing our symbol U for uranium. The top number is going to be your mass, so 235, and the bottom number is going to be your atomic number of protons, 92. And I can, of course, find this off the periodic table, you guys. If you look up uranium, it's number 92. Yield sign, okay? And then we know we're going to alpha decay it, so go ahead and add your alpha decay. We know it's He, 4 and 2. That's something you have to memorize. Put the plus sign. Now, this is the part we come up with ourselves. And this is a part that's pretty easy, so don't think of this as difficult. We need to say 4 plus something gives us 235. In other words, we can just subtract. So 235 minus 4 gives us 231. 92 minus 2 gives us 90. And then go back and check your math. Does 4 plus 231 equal 235? Yep, we did that one right. Does 2 plus 90 equal 92? Yep, we did that one right too. Now, in order to find the symbol, you're just going to look at the periodic table for 90, because remember, this is the number of protons. If you look, 90 is right here, and it is thorium, TH. So go ahead and write that TH, and you're done. You just alpha decayed it. You're good. Now let's look at beta decay. You're doing the exact same equation, and instead of doing the alpha particle, you're now going to write a beta particle, 0, -1, and E just standing for electron. You could write the fancy B for beta if you wanted to. It means the same thing, okay? You're going to do the math the same way. So 235 minus 0 equals 235. 92 minus -1 equals 93. So remember, when you minus a negative, it's just like adding a positive. And a lot of people get this one wrong. So always go back and check your work for beta decay, all right? So -1 plus 93 equals 92. Yes, that's correct, right? And then the top should be simple because it's the same number. If you look on the periodic table for number 93, it's neptunium. So go ahead and write NP. Gamma ray, easiest one by far. All you're doing for a gamma ray is you are going to substitute in that gamma ray instead of our beta, right? 0, 0, and the funky looking Y. Then you are going to do the math, but the math is all zeros. So guess what? It's the exact same thing. You started with uranium, you end with uranium. It's all the same thing. This is literally the easiest one to do. All right. If we are looking at our next thing, it says complete the following. And it just wants you to finish decaying it, right? So here we have iodine and we are beta decaying it. So just do the math. So 129 minus 129 equals 0, right? 53 minus 54 is going to give you a -1, or we can just say it in reverse, you guys. The 54 plus -1 equals 53, right? So make sure you check your math in both directions to ensure you have the correct answer. And then if you look on the periodic table for 54, you will see that that is Xe. So you can go ahead and look that up at any time you guys need to. All right, so it's right there. Okay, now the next one, this you're given now all of the reactants, and or you're giving the products and saying, hey, give us the reactants, right? Or really the front of the decay. So, or what are we decaying? So right here, we are using an alpha particle, and this is what it is resulting in. So let's just do the math. 239 plus 4 is 243. 97 plus 2 is 99. If you look for number 99 in the periodic table, you will get the ES, and then you are done. All right, and that pretty much concludes 4A, guys. If you have any questions, let me know.